In this session, we will be solving one typical Navier-Stokes problem. So we are given flow between two plates, two fixed plates. We are given the height 1.5 millimeters. We are given the pressure gradient 1.25 kilopascals per meters. We are given the viscosity of the fluid. It is a dynamic viscosity, 0.15 newton seconds per meter squared. Our coordinate system is located in the mid-channel and the flow is fully developed. Okay, the height h is measured from the center to the two edges of the plate. We are asked to find the volume flow rate through the channels. Okay, now right away we'll start our problems by solving the Navier-Stokes equation, which is given in this general form. Now obviously this is a 2D problem, so 2D problem. Right away, when it's a 2D problem, we directly know that our velocity, so we have three velocities in the x direction given in u, in the y direction in v, and in the z direction by w, which means all the terms containing w equals 0. Also, 2D problem implies all d by dz is equal to 0. This implies my du by dz equals to my dv by dz equals to my dw by dz equals to the d squared u by dz squared, which is equal to d squared u by dv by dz squared, which is equal to d squared u by dw squared. Also, my dp by dz is all equal to 0. Now, this is very important information. Why? Because when I say du by dz equals to 0, I'm able to say u is not a function of z. Also, dv by dz equals to 0 implies v is not a function of z. Similarly, dw by dz equals to 0 implies w is not a function of z. And finally, dp by dz is equal to 0 implies p is not a function of z. Now, this we did not start solving the problem yet. We're just stating what we know before we proceed and makes our problem simpler. Now, the flow is fully developed and it is steady. Steady means all the terms d by dt are equal to 0. Okay, now we will move forward and start solving this problem. Okay, so we start solving the x momentum. Momentum equation will be given in du by dt plus u du by dx plus v du by dy equals rho g minus dp by dx plus mu d squared u by dx squared plus d squared u by dy squared. Okay, now here we know that du by dt is 0 because d by dt is 0. Okay, we also know that we only have a velocity in the u direction. This implies v equals to 0. Therefore, v, which is 0 any times anything, is going to give me 0. Because it's two parallel plates and the distance is very, very small, 1.5 millimeters times 2, so 3 millimeters, I can consider the effects of gravity as negligible. Alright, so now I'm left with a few one nonlinear term here, which is u times the u by dx, and mu d squared u by dx squared plus d squared u by dy squared, and also I'm left with this. But from continuity, which is also known as mass conservation, which is given by rho into du by dx plus dv by dy plus dw by dz is conserved, so it's equal to 0. Now I know my dv by dz is 0 since it's a 2D problem, and if I take the density on the other side, so I'm going to be left with du by dx equals minus dv by dy. But we have mentioned that my v velocity is 0. We have no velocity in the y direction. So I have du by dx equals 0. In addition that this is going to help me solve the equation above, it also implies that u is not a function of x. It's very important. We'll see how we use that. So when I have du by dx is 0, obviously this term is 0, and if du by dx is 0, d squared u by dx squared is also 0. Therefore, I'm left with minus dp by dx plus mu d squared u by dy squared equals to 0, which I have mu d squared partial by dy squared is equal to minus dp by dx. Excellent. Now notice here we have stated u is not a function of x, and I have also stated u is not a function of z. So what does that mean? It means u is only a function of y. Therefore, the partial derivative d squared u by dy squared can be converted to total derivative. This will allow us to directly solve the problem in the next step by doing a separation of variable. We will move forward and solve the y momentum. Okay, so for the y momentum, what do I have? I have dv by dt plus v u dv dx plus v dv dy, this is v, this is u, v, equals rho g minus dp dy plus mu d squared v by dx squared plus d squared v by dy squared. Okay, dv by dt is 0. It is steady. All d by dt's are 0. We don't have a velocity in the v direction. We have stated that above. So dv by dx is 0, dv by dy is 0, and v is 0. Therefore, this is 0. We can neglect gravity because the plates are too thin. Gravity has no effects. V is 0. This term is 0. What am I left with? Minus dp by dy equals 0. Is this important? Sure. Why? Because from here I can say p is not a function of y. So what does this mean? It's important. I have p not a function of y, and I have stated that p is not a function of z. It means p is a function of x alone. What does this imply? I can say the partial derivative dp by dx is equal to the total derivative of dp by dx. And I have converted my huge mess up here to a simple problem that can be solved very, very easily. Okay, so we'll move forward. Now, to make my calculation simpler, what am I going to do? Alright, so I'm going to say mu du by dy squared equals minus dp by dx. Now, this is plus, we moved it to the other side. Yes, so equals to some constant, I'm gonna call it CO, and then I can say d squared u by dy squared equals CO over mu. Alright, so I have a very simple integration problem here. So I integrate once and I'm going to get du by dy equals c0 over mu y, right, plus c1, and I also have u equals, second time taking the second integral, I have c0 over 2 mu y squared plus c1 y plus c2. Now, what do I have here? I have the general equation of the velocity anywhere between the plates. I'm left with two simple problems, which is finding my constants. To find these constants, I have to set two boundary conditions. Okay, so you can be creative when it comes to boundary conditions, but I like to keep it simple. So I will say when y equals h, I have u equals to 0. Because when the fluid is going through the plates, when y equals h, at the edge of the plate, the fluid will stick to the plate and its velocity will be 0. This is one boundary condition. Second boundary condition, I have at y equals minus h, the bottom. Again, I have u equals to 0. Excellent. So I have two boundary conditions which can help me easily solve the two constants, right? So we're going to go and start replacing. Alright, so first boundary condition at y equals h, what do I have? U equals 0. Okay, so what does this imply? Right away you can see if I replace here 0, h and h, let's see what we're going to end up with. So I'm going to have 0 equals c0 over 2 mu h squared minus c1 h, right, minus plus c2. Second boundary condition, at y equals minus h, I have 0 equals c over 2 mu h squared. Now I replace minus h, so I'm going to be left out with, okay, let's consider this plus, this is minus c1h plus c2. Okay, Now by substitution, you will find that C1 equals to 0 and C2 equals minus C0 h squared over mu. You replace in y, in u, you will get C0 over 2 mu y squared minus C0 h squared over 2 mu. This is solved. Furthermore, we replace our constant C0, which was dp by dx. We're going to end up with u equals h squared over 2 mu dp by dx. We factor the y's, we're going to end up with h squared minus 1. Now, the question. We did all this, but we have not solved the question yet. Find the volume flow rate. Across the channel. What's the volume crossing the channel? It's given in Q. The boundary conditions, I have here minus h and here I have plus h. I have integral minus h to plus h u dy. Okay, so it's equal minus h plus h. I replace my u very simple integration. There's nothing complicated here. U cubed over 3h squared. It's straightforward. You end up with q equals minus h cubed over mu dp by dx 2/3. If we replace our dp by dx, which is given by 1.25 times 10 to the 3 newtons per meter, and we are given with the mu at 50 newton second per meter squared, and we're given our height at 1.5 millimeter, my flow rate will be minus 5.63 times 10 to the minus 6 meter cube per second per meter. This is the end of the problem. Now, if you ask a computer to solve this for you, it will not give you this direct answer, because what the computer is going to do, it's going to take the channel and it's going to break it to grids and meshes, and it's going to apply some kind of mathematical numerical method to solve this problem. And moving from each node to the other through the calculation, a small error will accumulate and your final answer will not be exactly minus 5.63. The reason behind this, that this is a problem that we can solve by hand. Now, most of the problems, as soon as they get complicated, cannot be solved by hand. Right? So that's our typical Navier-Stokes problem.